Okay, we have this problem. A cylinder of radius r and mass m is at rest at the top of a ramp of height h and length l. At t equals 0, it starts rolling down without slipping. Calculate its velocity and the time elapsed when it reaches the end of the ramp. Okay, so we have this cylinder of radius r and mass m, which is initially at rest at the height h, and in the initial instant it starts rolling down the ramp until it reaches the end of the ramp here, and at this instant it will have a linear velocity v, and also it will have an angular velocity omega. We know that this angular velocity will be related with the linear velocity by v over r. Okay, and we also know, let's call L the length of the ramp. We also know that there's going to be we can apply here the conservation of energy. The energy at the beginning is going to be the potential energy due to gravity plus the kinetic energy initial. Let's call it U initial and K initial. And the initial potential energy will be N times G8. And the initial kinetic energy of the cylinder will be 0 because the cylinder is at rest initially. And since there is since we can apply conservation of energy, we know that in the end the final total energy will be the sum of the final potential energy, which will be 0 because the height in the end is 0. So there is no height here. We're taking all the heights, we're measuring all the heights with respect to this level, and in this case the height is 0, so the potential energy at this position is 0, plus the kinetic energy in this final situation. The kinetic energy here will be the sum of two terms. One is the translation kinetic energy, which is 1/2 of m times v squared, plus the rotation kinetic energy, which is 1/2 times I, which is the momentum of inertia of the cylinder, times omega squared. Here, in this last term, we have to take into account two things. One thing is that the momentum of inertia of the cylinder can be expressed in terms of the mass and the radius of the cylinder as 1/2 times m times r squared. And also we can take into account that as we have written before, there is a direct relationship between the angular and the linear velocity of the cylinder. So we can substitute these two things here, and we can write the second member of the equation. I will write the first member also here. We can write the second member of the equation as 1/2 m times v squared plus 1/2 m times r squared v squared over r squared. So r squared vanishes here. We also have the mass vanishing here. So finally we get G8 equals, this is 3/4 v squared. Okay, so I will write it like this. V squared equals 4/3 of g times 8. I will write it in this form. I will give the expression of the square of the velocity, And from here we can write v equals square root of this, which is 2 over square root of 3 square root of g8. And this is the answer, this is the solution that we were looking for the velocity of the cylinder when it reaches the end of the ramp. Now in this second part of the video we are going to derive the time elapsed when the cylinder reaches the end of the ramp. I have written again here the expression that we have got relating the square of the velocity in the final instant with the height that the cylinder has gone down from the top of the ramp. So I want to emphasize the fact that this equation, this formula, is totally general. If we consider a given distance let's call it y, okay? A given distance vertically for a given instant of time in the middle of the ramp, for example in this position, in this instant of time, we can write exactly the same expression substituting the h by the y. So we could write that the velocity, let's call u the velocity at this instant, u squared equals 4/3 of g times y. And y can be a distance whatever from 0 down to 8. It's totally general, the expression. I want to emphasize this. So we can take the differential of this expression and we can write 2u differential of u equals 4/3 g differential of y, where y is this axis, the vertical axis pointing downwards. Okay. Now let's define. I will draw it in green. Let's define the axis of the direction along the ramp, the direction the cylinder is taking along the path on the ramp, and this direction we call it x. Okay. Now we can see that the velocity at a given instant u equals the time derivative of x. Okay, but on the other hand we can relate a differential of x, a differential along the axis x, with a differential along the y-axis by means of the sine of this angle theta. Okay, sine of theta, which is this angle, equals 8 over L. And we know that if we take a small shift along the x-axis, let's call it differential of x, this small shift will correspond to a corresponding shift vertically along the y-axis, so that the relationship between both differentials is that differential of y equals sine of theta times differential of x, which is 8 over L differential of x. Okay? Now, from this expression, we get that differential of x equals u times differential of time. And if we plug this expression here in this equation, we get that differential of y equals 8 over L u times differential of t. And we can substitute this expression that relates the differential of y, the vertical coordinate, with the differential of time. We can substitute this in this expression. Okay, so I will use red again. We can get 2 times u differential of u equals 4/3 g h over L u differential of time. And we can cancel out u, the velocity. So we get differential of u equals 2/3 g times h over L differential of time. Well, this is the equation I wanted to get to that relates the differentials of the velocity at a given instant, whatever, and the differential of time. This is a differential equation that is straightforward to integrate, and we can integrate it taking into account the initial conditions. Initial conditions are that the initial velocity is 0 and the initial time is 0. So applying these initial conditions in the integration of this equation, we get that the velocity alongside the ramp in an instant or whatever equals 2/3 times g times h over L time. Okay, so this is the general equation for the velocity as a function of time. So we see this is a uniformly accelerated movement. The acceleration is the coefficient that is multiplying the time, and in particular we can derive from here that the time equals, solving for time, okay, equals, let's see, it's 3 times L divided by 2 times g times h times the velocity, and in particular the time in this final instant will be the value we get when we substitute u by v, which is the value that we got from the first part of the problem. Okay, here we have that v equals 2 times g times h divided by 3. So if we substitute u here with this value, okay, I will write it here, we get that time in this instant, in this position, when the cylinder has got to the end of the ramp, let's call it final, okay, equals the time elapsed for the whole descent along the ramp equals 3 times L divided by 2gh, and then we have 2 times the square root of g times h divided by 3. We can cancel this here with this here. Okay, we can cancel this 2 factor here with here, and finally, okay, I'm trying to be careful not to mistake. Finally, we get, I will write it here, that the time that the problem was asking for equals, well, I can even cancel this 3 factor here, so it is a little of a mess, but I will try to sort it out here. This is equal to square root of 3, and then we have L over square root of g times h. Okay, so this is the answer for the second part of the problem. The time the cylinder takes, it takes the cylinder to go from the top, being initially at rest, to the end of the ramp.